So we are getting started on thermodynamics. We will talk about enthalpy and entropy and Gibbs free energy in our thermodynamics. We're sort of leaving equilibrium behind, but not really. Equilibrium is still part of our thermodynamics discussion. We probably won't solve many rice tables in the next couple of weeks, but we will still talk about equilibrium and K values and what they mean. We're going to use our thermodynamics discussion to answer the question, does a chemical reaction occur spontaneously? When we as chemists say the word spontaneously, we mean, does it occur naturally? So if you have sodium chloride, solid sodium chloride, this is table salt, does that sodium chloride spontaneously become sodium salt and chlorine gas, sodium solid, and chlorine gas? Does it go to... No, we're going to say that reaction is non-spontaneous. It does not naturally happen that solid sodium chloride table salt could spontaneously at any point become sodium metal and chlorine gas. This is glucose. Glucose is a solid sugar, can be considered a solid sugar. It can be oxidized, combusted with oxygen gas to become CO2 and H2O. That's a possible thing that glucose could do. This is a possible thing that sodium chloride could do. We've said sodium chloride doesn't actually do this. We will say glucose really does do this. This is a spontaneous reaction for glucose to be oxidized in this way to break down into CO2 and water. Our bodies do that all the time. So I said we're leaving equilibrium behind, kind of, sort of, but not really far behind. We're trying to answer this, does it occur naturally, does it occur spontaneously? What a chemist actually means when they say that is, what's the size of K? If something occurs spontaneously, it's going to have a large K, lots of products at equilibrium. If something is non-spontaneous, very small K, not a lot of products at equilibrium. So if I look at the K value of these two reactions, negative 35, that's a tiny number. Is it possible that a little bit of this product exists in solution? Yes, not just possible, it is likely. It does happen. But negative 35, it's a tiny, minuscule amount. Positive 350, that's kind of even ridiculous to think about, right? So that means we've got almost exclusively a tiny fraction of reactants might be left over, but almost exclusively products at equilibrium for this bottom reaction. That's what we mean by spontaneous and non. So we can look at K values and say K greater than 1, spontaneous, K less than 1, non-spontaneous. Excellent. We talked last semester about delta H. Do you remember what delta H means? Delta H is enthalpy. It's heat energy. So sometimes it's confusing. Why do we call enthalpy the symbol? Why do we give enthalpy the symbol H? Well, it's heat energy, and H helps me remember heat energy. That's H. Okay. So if I look at this reaction, my last semester learning would allow me to call that thing endo or exothermic, this top one. Negative delta H means exothermic. While we're labeling, the next one with a positive 411, that's endothermic. And the bottom one with a negative 2808, that's exothermic. In general, exothermic reactions tend to be spontaneous. Is that always and forever? No. But in general, exothermic reactions tend to be spontaneous. So this reaction that's exothermic, it has been measured to be spontaneous, have a large K value. This reaction that's endothermic, it's actually the same one from our previous slide. I think I said exo. This reaction that's measured to be endothermic has been measured to be non-spontaneous, very tiny K value. This reaction that's exothermic is spontaneous. It has a large K value. In general, exothermic reactions tend to be spontaneous. Is that always and forever? No. Can you be exothermic and non-spontaneous? Yes. Can you be endothermic and spontaneous? Also, yes. In general, exothermics tend to be spontaneous, but this reaction is endothermic, positive. Endothermic, it's a positive delta H, and this reaction is spontaneous. Ammonium nitrate is soluble in water. It dissociates into those two ions. When you put ammonium nitrate in water, it dissolves, it dissociates. All ammonium ions are soluble, all nitrate ions are soluble. Yeah, this fits the solubility rules. It's soluble. The weird thing is, when it dissolves in water and dissociates in water, the beaker actually feels cold to our hand because endothermic reactions absorb heat from the surroundings, like our hand, and exothermic reactions release heat into the surroundings, making the beaker feel warmer. So these guys would cause a beaker to feel warmer if they are happening in a beaker spontaneously, while this one causes the beaker to feel colder. Something additional needs to be considered. So it's not all about delta H. In general, delta H negative is spontaneous. But sometimes when delta H is positive, the reaction is spontaneous. Something else needs to be considered, and we're going to talk about that something else on the next slide. But while I'm here, I've told you I don't love memorizing, so I take any shortcuts that I can. How do I remember that endo and exo, how do I remember what's what? Truly, I swear to you, the thing that helped me back in the day was ENDO is 4 letters, and PLUS is 4 letters. EXO is 3 letters, and NEG is 3 letters. I don't know why I stopped there. I don't know why that made sense to me. But endothermic reactions have positive delta H's. Exothermic reactions have negative delta H's. Heat is exiting. When you have an exo, heat is entering, I know, when you have an endo. That's how I remembered these things for real. Endo, enter, exo, exit, plus minus the number of letters helps me. Okay. Back to where we were about something additional needs to be considered to determine spontaneity. Delta H is a good factor, but it's not the only factor. Another factor is the spread of energy. So enthalpy is heat energy. A new term is entropy. And entropy is given the symbol S because it's about the spread of energy. If you have this apparatus here, whatever this is called, and you have a gas trapped in one side and you open that stopcock, naturally those gas molecules will spread all over that whole apparatus. It is spontaneous for them to spread in that way. It is non-spontaneous that once they are spread, they will spontaneously assemble back into one side. No. Once you have spread out the energy, you can't bottle it back up. Imagine if you have a balloon that is full of air and you let that balloon go, if you didn't tie off the part where you blow it up, you let that balloon go and you let all the air escape. Could you imagine trying to recollect the exact same air molecules that went into that balloon and put them back into that balloon? No. The laws of nature and our observations tell us that is not a possible thing to do. Taking spread out energy and making it more organized, not very reasonable. Okay. Entropy is measured spread. Yep, I actually already said that. Okay. We would say this state, our initial state, has a certain measure of entropy, S initial, and this final state has a certain measure of entropy, and the spread is greater in the final than it is in the initial. S final minus S initial would give us a positive value for the change in entropy of this system, because final has more entropy, the final has more spread out energy than the original, the initial. Yep. Delta S reaction is final minus initial. Yeah, it's positive. Yeah, I said that. If the change from initial to final results in an increase in energy dispersal, the reaction is spontaneous. Okay. If we talk about physical states for a second, physical states, everything on the planet has a certain measure of entropy, an intrinsic entropy value. Solids have smaller spread of energy than liquids do, and liquids have smaller spread of energy than gases do. Gases are very spread out compounds. Very large distances exist between one gas molecule and the next gas molecule, especially compared to in a liquid and a gas. Spread out, less spread out, kind of compact energy in our gas, liquid, solid backwards way. If you're melting water, going from solid to a liquid, that's creating more disorder by becoming a liquid. This process has a positive delta S, right? Delta is always final minus initial. Don't forget that. Delta is always final minus initial. Okay, so entropy is a state function. Enthalpy that we learned about last semester is a state function, but entropy is also a state function. A state function, it doesn't matter how you get there, but the change is the same. Blue hiker, red hiker. Blue hiker took a shorter path, red hiker took a longer winding path, but both of them ended up at the top of the mountain. They took different paths, but both of them ended up at the top of the mountain. So their change in altitude is the same overall. We drew last semester some enthalpy plots where we would have reactants on one shelf. Maybe we go up to intermediates on another shelf. And then maybe we go down to products on another shelf. This overall plot was this reactant goes to intermediate kind of thing. But this overall plot, all that you cared about overall was how reactants and products compared. The delta H overall from reactants to products. Who cares how many intermediates you went through? That's a state function. All right. What's next? Yep, entropy. We added entropy to the list if you didn't notice that. Okay, so we will have to make qualitative, I always have to hesitate with that word, we will have to make qualitative observations where we look at a reaction and see, did it go from solid to liquid? Okay, delta S is positive for that reaction. Did it go from liquid to gas? Okay, delta S is positive for that reaction. Did it go from gas to liquid? Okay, delta S is negative for that reaction because I'm creating more order. We will have to look at equations and make qualitative observations about entropy changes for a reaction, but we will also have to do calculations and quantitative measures of entropy changes. Delta S calculations are just like delta H calculations, that it's the sum of the sum of entropies, it's real hard to say that right word, the sum of entropies of the products multiplied by their coefficients, minus the sum of entropies of the reactants multiplied by their coefficients. So as we often do, we'll give you a standard equation, A plus B with these coefficients yields C plus D with those coefficients. So what I'm saying is, the coefficient in front of C times the standard entropy of compound C, plus the coefficient in front of D times the standard entropy of compound D, sum together the whole entropy of the products, and subtract out the total entropy of the reactants. The coefficient times the value from the back of the book, plus the coefficient times the value from the back of the book, right? Let's do it with an actual mathematical example. What's the standard entropy change for the following reaction at 25 Celsius? That would be delta S of the reaction is equal to 2 times CO2, that's the entropy of CO2, I should probably put a little S, CO2, minus, because that's my only products, 2 times S of CO plus S of O2. The coefficient of 1 doesn't matter. Note, the state of the compound is very important. When you look in the back of the book for values, or when you look in the ALEKS data tables for values, you're going to see various compounds back there. Maybe not a lot of options for CO2, but you're going to see various options back there that have different physical states, and those different physical states matter because you have different enthalpy values based on the physical state. Okay. So I've looked in the back of the book and come up with these entropy values. So now it just becomes a plug and chug. Delta S of the reaction equals 2 times CO2 is 213.6. Weird units here, but joules per mole Kelvin, or K-mole, minus 2 times CO is 197.9 joules per K-mole. That's Kelvin times moles, plus 205 joules per K-mole. And so it's add and subtract, and make sure you do your order of operations that you multiply first and all that kind of thing. Yeah. I do that, and I come up with negative 173.6 joules per kmol. Yep. Delta S for this reaction is negative. I'm going from 3 moles of gas to 4 moles, I'm going from 3 moles of gas to 2 moles of gas. I can't count. 3 moles of gas to 2 moles of gas. It is becoming more ordered when I only have 2 moles of gas instead of 3. I should be able to look at this reaction and say, yep, it's going to be a negative delta S, and then I quantitatively calculate it. Yep, it's a negative delta S, right? Right. All right, a couple of qualitative observations. How does the entropy of a system change when you condense water vapor? I'm trying to train you up that you think equation when you see words like this. Water going to water, but it's condensing water vapor. That's gas becoming liquid. Pictorially, here's what I got for you. Gas becoming liquid. It is becoming more ordered as a liquid. So delta S of this reaction is negative. In general, spontaneous processes need to have a positive delta S. It is possible that a reaction be spontaneous and have a negative delta S. In order to do that, it means your delta H has to be the right sign, and it's hard for me to want to say more and not say more. But in order for this reaction to happen, heat must leave our system. Yeah, it's got to be exothermic. We're going to talk about all the signs a lot more, but it's got to be exothermic in order for that reaction to be spontaneous. Is it spontaneous at room temperature for this to happen? Yeah, it actually is. Gas will become liquid water at room temperature. Yeah. Okay. Forming sucrose solution from crystals of sugar. That means solid sucrose becoming aqueous sucrose. You've added water to this thing, and it has started to associate with your sucrose molecules, but that sucrose still does not dissociate. It has associated but not dissociated. Going from a solid to an aqueous solutions are absolutely more disordered than they were before. The energy is more spread out than it was before, so delta S is positive for this guy. All right, heating hydrogen gas from 60 to 80 degrees Celsius. If you have gas that exists at cooler temperatures, the vectors are shorter than at higher temperatures. What the heck? This is not physics class. At cooler temperatures, the vectors are shorter. That tells me they're moving with less speed. If I heat the gas, the molecules start moving at higher speeds. If I look at what's called a kinetic distribution plot, at this lower, cooler temperature, the average kinetic energy, the average kinetic energy is at this hump. There are some that have greater kinetic energy. There are some that have lower, but the average kinetic energy of molecules is this. If I heat that gas, it spreads out. Do you hear that word there? It spreads out the distribution of energies of my gas particles. And more spread energy means positive delta S. More spread means positive delta S. Almost done. So, one little thing about the more atoms in a molecule, the greater the entropy. If all else is the same, this is C6H6, this is C2H2. If this is a gaseous molecule at a certain temperature, this naturally has higher entropy than that because this has more molecules. We can get into a lot of deep discussions about why, but we're not going to. That's not where this class is focused. But more molecules, more atoms in this molecule means more spread out energy. Okay, conversely, if I have one C6H6 molecule versus 3 C2H2 molecules, this is the same entropy, but all of a sudden I need to take this number and multiply by 3 to know the entropy of this system as a whole. So more molecules, even though it's the same number of atoms, 6 carbons and 6 hydrogens in both cases down here, more molecules are going to have more spread out energy. More atoms within a molecule has more spread out energy, but then more molecules has even more spread out energy than that. Maybe that makes sense? All right. Welcome to Entropy, Thermodynamics. Whoop, whoop.